Hey guys, hey guys, let's look at this problem, maximum depth of binary tree. We're still in the section of recursion. Okay, we're given a binary tree, finding its maximum depth. Like this tree, the maximum depth, of course, is 1, 2, 3. So now let's write the code. Oh, of course, we start with the recursion. This kind of thing's maximum or something. Maybe it just could be simply solved by recursion. Okay, so our base case for this recursion is when we got to a leaf node, right? When there's no left and no right, then the depth should be 1. Okay, so but we can consider there's a null. So yeah, the best case is that we will go to null. The depth should be 0. So okay, const get. I just say with the underscore max depth node if node equals null, return 0. In the other case, we return mathmax node left. Oh, sorry. The max depth of left plus or max depth node right plus 1, right? And we just return it. Return max depth node. Let's run code. Oh, runtime error. Node is not defined. Wait a second. God, it should be root. Okay, we're accepted. So actually, let's comment this out. Our recursion time actually every node is traversed once, accessed once, so it's on space. Actually, we are having a stack, right? We have to store this because this is a stack. We have to keep a stack of the function call of mathmax. It is not max depth, so it is now tail recursion. So actually, this will be a stack of a mathmax call. So that will be the longest. This will be longest path to live. So actually, it should be worst case should be on, but averagely, if it is balanced, so it will be actually if it's balanced, I think it will be just O log n. Now let's take another with a it's not super, but usually for tree traversal we have BFS and DFS, right? So we use a BFS first. Remember, for BFS it should be use a queue. Okay, so we have a queue. Let's first put root in it. And of course, we also have a let depth equals how to say. So each round will get the elements from the queue and push it. So the depth should be 1. Of course, if root wait a minute, if it is null, we don't plus 1. Okay, so actually depth, we could say depth set to 0, and we put the root node in the queue. So while there is an element, we will get the element out, right? So the first one well, Q. Wait a minute. Null. If it is null, if it is null, it must be if it is null, we don't do anything. Plus, okay, so we get the head item of this queue. Okay. Let item equals queue shift. Oh, no shift. You can say use while. While let items queue shift. If item is not equals to null. If we need to keep the flag. Let has child equals false if it is not null. Wow, this is weird. Okay. We'll just return. If root is null, we return 0. Now depth should be 1. Okay, so the root must not be null. There will be no null case. So if item left or item right, then as child equals true. Oh, we can say make it concise like this. And then we can push it back to the queue, right? Push item left. If item is null, we continue. We continue, and the has child. Okay, we queue push left, and then queue push item right. Ah, no. God, we shouldn't push null in it. Okay. If item left, if there's left, we push it. If there's item right, we push the right. And yeah, actually has child, we can remove it. Okay. When it is around, if there's queue length is bigger than 0, okay, with depth plus equals 1, so should be 0. Yeah, because okay, for the first round, root is there, so is bigger than 0, so depth is 1, right? And then we shift it and we push them in, and yeah, finally we can return depth. Let's run the code. Ooh, runtime error, unexpected identifier. Oh, my mistake. Let item. Well, item. This is okay. Ooh. Item equals shift. Console log item file. Run the code. 3, 9. Okay. Why there is log while q. God. I'm too old to do the algorithm thing. We should shift them all out and then push them in. So how can we solve this problem? We can create a new array, but that's not maybe that is not a good. Maybe that is not good, right? Okay, so if there is element, we push a null in it, and then we shift. When we shift, we push, and until we get an item is true. If it's not null, so yeah, okay, this should be okay. Yeah, push in and a separator. Right? Okay, we submit. Okay, accepted. BFS. So the time should be. It's the same. Every node is actually accessed once, so it's when space. We use the extra array to hold the numbers of each level. So actually, the maximum. How the maximum is actually, if we consider it's a full binary tree, so it should be ON. So it's still ON. BFS. This is BFS. Okay, let's try another one. Is depth first, which is DFS. DFS stack. Okay. DFS stack. Okay, this if it is null, we still return 0. But now we have a stack. We push it in. So stack is we push, we pop and then we push. And then we get the element, and then we pop out. That will be depth first. DFS. We will get the amount of maximum maximum depths. We actually need to store. We actually need to pass down the maximum current depth, right? Okay, so actually, let max depth equals 0. Let current depth equals 0. Okay, the stack, we push the root in. So while there is stack where there is elements in the stack. Should we push null? Actually, no, because we're using DFS. The element will be it will stop at the leaf node, so we don't need to push null. Okay, we don't need to shift them all. Okay, so we just set top equals stack pop. Okay, when we pop one, then we say recurrent. Oh no. When you pop one, we get it out. So current depth plus 1. If top left, and the top right, if this is a leaf node, then we say max depth equals max. We just update the maximum, right? Max depth and the current depth. If this is the case, then we will no. Let's push to 1 to 2. Okay. No, we should keep the track of not only the element node but also the depth. So for the root, the depth is 0, 1. So this is 1. Okay, so we get top. We should not plus this one. Okay, this is current depth. If top, there is no top and no right, then should be, yeah, this is right. If not leaf nodes, we will stack push. If top left, it doesn't matter the order of the children. So if top left, then stack push top left and the current depth plus 1. We copy this code and then we top right. We still push top right. Yeah, it means we keep a stack of not only the node but also the data we want to collect. Okay, so while stack is, yeah, we can do this recursively and it's done. With this work, let's do some check. So for 3, 9, 20, we first got 3, 1. Okay, we pop it 3, 1 because it has left. So we got 9, 2, 9, 2. Okay, it should be working. God, there's a typo here. Oh, God. Depth is not defined. Depth. Where is depth? 970. Return depth. Oh, God. This is the problem of copy and paste. We submit. It's accepted. But yeah. This is DFS. The space, the time is also every node is traversed once, so SON space. Space is actually, we keep this stack of all the elements from the root to the leaf. So actually it's O log n. Let's just submit it and take a look at the fantastic submissions like this one. Wow, it's so perfect. Huh? This is a recursion. This is a recursion submission. Yeah, we've why it's so fast? It's weird. Let's take a look at our submission. Just whoa, I've tried this like 16 days ago. I didn't know. First one is recursion. Huh? No, not this one. This one? Yeah, which is return. This is the same. But it's not fast. Anyway. I think the definition of this function is. Anyway, we finish this problem in 3 ways. First one is recursion, but attention that it's not tail recursion, so it will cost us extra space of the call stack. Next one, we try BFS. BFS, we use a queue. Every time we use BFS, we use queue to process the elements in the same level. The one problem is that we need to add a separator in the queue to know that where is the end of each level. Like we are shift elements out and then we push their children in the rear. We need to know where to stop, so we use the null to check. And the good thing is that if we use a null, we can use a while loop to just shift it to check if it's a null. If it's null, we just stop. Okay. I think there is a problem here. I'll take a look at it later. Last one is DFS. DFS is depth first search. It should be a stack. In our case, we stack not only the element but also the data we want to collect, which is the depth. So for the first root, we just say, okay, your depth is 1, and then we push to the children of the root, say your depth is 2, and when we meet the base case, which is the leaf node, we update the max depth by comparing the maximum depths and current path. Yeah, that's all for this one. Wow, it's a lot of code. Okay, see you next time.